Welcome to episode 6. I'm pretty sure we're up to episode 6 of Dark Chatter, which is our, well, I was going to call it a weekly series. It's not a weekly series. It's an amount of times in a month series where we talk about different topics, sort of vaguely in the world of dark matter, particle physics, phenomenology, astrophysics, this whole world that's sort of fun to mesh together. We get into that stuff. So this week we're joined with Innes Bigaran, and would you like to introduce yourself?
Cool. Hi, I am a PhD student here at Melbourne University, and broadly I study flavor physics and neutrino physics here. So I work in particle theory. Yeah. Cool. So not quite dark matter, but dark matter adjacent.
Sweet. And I'm Zac Picker. You may remember me from such films as the other ones I did so far. I'm more of a black holes sort of astroparticle guy, so I don't really know anything about muon flavor physics. I mean, I've done particle physics courses. Nominally, I'm in the particle physics group, so I should know things. And this is a good opportunity to learn some things for me, maybe. So I think maybe, well, I was wondering how much research I should do before this, but I decided to stay a little bit ignorant because maybe that makes the interview more exciting and tests your explanatory skills a bit. So that could be fun. I'm sure.
Yeah, we'll see.
So we've had 2 big flavor announcements in the last month or so. One from the LHCb and one from FNAL at Fermilab. Do you want to take us to the first one, the LHCb one?
Yeah, cool. So the one at LHCb was an update of a branching ratio. So RK and RK star are some really well-known, well, now they're quite well-known anomalies that already exist in B meson physics. So RK and RK star, they just refer to the difference between the branching ratio of the B meson to B meson from K to mu and the B meson from K to E. So the ratio of the muon to the electron mode of those decays. So theoretically, the only distinction between those 2 decays should be the basically the phase space that's open from either a muon or an electron decay. But realistically, so both of these ratios are predicted to be about 1 in the standard model. But realistically, what we end up with is a value that seems to be quite different from 1, which indicates that perhaps there is some lepton flavor non-universality that may exist in some beyond the standard model physics. So perhaps there is BSM physics that couples differently between the muons and the electrons. And this has been quite a persistent anomaly now. I can't remember exactly when it first emerged. I think it was around 2013, and has been measured at the electron-positron colliders as well as at the LHC through LHCb. So it's interesting. The significance went up. The overall value moved slightly closer to the standard model, but the error bar shrunk. So it's a good sign in that, you know, it's a more significant anomaly, but, you know, we're cautiously optimistic, as all of Twitter told us after the announcement.
But just for those of us who aren't as good at particle physics, just quickly run through the real fundamental of physics, you know, like what's a B meson? What is this actual process? You know, what does it mean that the electron and the muon are doing something differently?
Yeah, this is a really good question. Thank you for pulling me back for a second. So a B meson is, so meson is a couple of quarks together. So it's a quark-antiquark pair that are bound together into some bound state called a meson. So if one of those quarks or antiquarks is a B, so a bottom or a beauty, depends on what you want to call it, it's a B quark. If one of those quarks is a B, it's called a B meson. And they're particularly interesting because Bs are quite heavy. So relative to other quarks in the standard model, the B quark is quite heavy, which makes it a lot easier for a lot of us to use certain approximation schemes. If something's very heavy, in the same way that if I, jump on the floor, I can say that I am traveling a certain distance up, and I can measure gravity based on the height that I travel. But I don't actually ever have to think about how much the Earth has traveled as a result of the interaction between myself and the floor, because the Earth is very, very heavy. So the Earth is essentially not moving at all. And you would never sit there and try and measure the recoil of the Earth from me jumping on the floor. So it's the same sort of thing that applies here for a B quark. So the B quark, being so heavy, means that we can do quite precise measurements when it comes to understanding the physics of the different decays or interactions that are occurring with B mesons. So theoretically, in the standard model, so the B meson decays, whatever, but then in certain final states, you have different leptons. So the idea is that in the standard model, the electroweak bosons, so the weak force, treats all leptons the same. So basically says, all right, we've got leptons, they should couple the same. The only difference should be whether or not they're big enough that the amount of energy available at the decay point is big enough to create like electrons or muons, because the difference between the electrons and muons are just the mass.
Right.
So if there's a lot of energy there, we can make a lot of them. Beg your pardon?
In the standard model, the only difference is the mass for this process.
In the standard model.
Right. But
in the standard model,
there's some extra difference on top of that.
Exactly. So there's some extra difference there, and that's why the ratio is so far away from 1. So maybe there's something there that distinguishes between electrons and muons.
Okay, yeah. So I guess the word for that is flavor non-universality, something like this, right?
Yeah.
Is that the right usage of that?
Yeah. So in the standard model, lepton flavor is universal. Like the couplings to different lepton flavors are universal, whereas beyond the standard model, there is hint of lepton flavor non-universality.
And so there's another experiment that also just released some results about this. The one from Fermilab. Can you take us through that one?
Yeah. So this one's kind of my favorite at the moment.
Yeah, sweet.
So the G-2 experiment at Fermilab was basically trying to look at how muons interact with magnetic fields. So like I said before, you've got your electrons and muons are very similar, difference in mass. The muons are heavier than the electrons. And what's interesting as a test of quantum electrodynamics is measuring the way that these particles interact with magnetic or electric fields. So according to like classical physics, so like classical, by classical, I mean like the stuff that was originally in quantum mechanics. The prediction was that the way that the electron or muon would couple with the magnetic field would be about a strength of about 2. So that's why we refer to G-2, because G is the coupling that we see between the spin of the particle and the magnetic field. And we're measuring the difference between G and 2. And what that originally was parameterized as is the loop order effects that will be occurring at that vertex. So the more quantum fluctuations, I guess you could refer to it as, that are occurring due to higher order interactions that are occurring between the field and the spin. So we predict in the standard model a value for G-2, and we observe a value of G-2 using the Fermilab experiment. So the way that they do that is they shoot a bunch of particles at a target. They then end up with a bunch of pions, and pions decay preferentially into muons. And then you can look at the way that those muons fly around, and they decay again, and they decay into a positron and a neutrino. You can't detect a neutrino, but you can detect a positron. And when you look at the direction and the rate at each direction of the positron emission, you can measure from that basically how the muon was rotating before it decayed. So from that, you can tell something about the magnitude of that rotation. And that magnitude gives you some information about this coupling between the spin and the magnetic field. So this was an established anomaly. It's kind of been around for a bit. So we knew that the standard model prediction for the G-2 was not 100% consistent with what we were seeing at the earlier Fermilab experiment. Sorry, not Fermilab, it was at Brookhaven. And then now the newer one we find is also showing some deviation between the standard model and what we observed. So perhaps this is also indicative of some sort of new physics in the muon sector, which is why we're liking muons at the moment.
And so this was in the news because it passed the sort of 4 sigma threshold, right?
Yeah.
Can you take us
4.2.
through 4.2? Yeah. Can you take us through like what are the main sources of uncertainty? What are the systematics? What's the statistical error like? How does this work? How do you calculate that anyway?
It's a very good question. So I'm not super familiar with the systematic error of the experiment itself. So my understanding is that they have done a whole bunch of checks. So the major thing that they did in order to try and minimize the amount of bias that there was in actually this measurement was to keep the data blinded. So they didn't give anyone any actual access to viewing the final data until I think it was February, where they used this Zoom conference call to put everyone who was involved in the experiment onto a conference call and unblind the data together so that then everyone could see at that point the significance of the analysis that they'd done.
Yeah, I saw that on the announcement video that they did. That was very exciting.
Yeah.
I love a good support wheel for a discovery, you know?
I still have like in the back of my mind the like the Higgs announcement when they announced it.
I always watch that. It's such
like
a good video.
I just remember seeing like on the live stream because I was in first year uni and I had no idea what was going on when they were talking about systematics. And I just immediately saw like people crying in the front row, like, you know, old tough looking men like weeping over a plot on the screen. And that was insane. So it's the same sort of vibe here. I don't know. But yeah,
you weeping, but that would have made a good video. We can.
It really would have been.
Like, you know.
I wish I could weep on command, but I've been working on it. It's not really working that well, but
maybe by the end of the PhD we'll be there.
Yeah, I've got a good 9 months or so of weeping practice to get in.
Yeah,
but yeah, definitely. It was a very exciting announcement, and yeah, they did incorporate a bunch of different things to be able to try and minimize that error. Some people have questioned the anomaly because there also exists a couple of different ways that in the standard model we can predict what the value of the standard model G-2 is.
Right. So
some people use certain techniques in QCD sum rules in order to be able to calculate it. So this is one method, details of which I am not very familiar with because I'm definitely not a QCD person. But people do some very, very intense calculations in order to predict the standard model value of G-2.
Well, I mean, that's good. Sorry, finish your thought.
No. And other people use some other very complicated ways of calculating the G-2 standard model contribution. And it turns out that a bunch of people have done it one way for years. And then at the end of last year, people came out with a new measurement. It's called the BMWC measurement, colloquially amongst the community. We joke that it's actually just a, advertisement for BMW. But these are the names of people who did the analysis. And that one, if you were to consider that as the standard model prediction and compare that to the experiment, the anomaly is much smaller. But the difference is that that particular method has only been used once in the literature, whereas this other method has been used a lot of times. So depending on who you speak to, people are less or more optimistic about the validity of the standard model one.
Right. Well, I mean, I'm speaking to you right now. So I guess my question for the segue is like, what is your expertise? Like, what's your role to play in this sort of muon anomaly world?
So generally, my role has been to look at the potential for beyond the standard model contributions to these processes. So perhaps there is some new physics that exists that interacts in the correct way, preferentially, ideally to the muons, and that this leads to a contribution to the process that would be consistent with the anomaly. So the real major one that I worked on is using scalar leptoquarks. Okay. So in the standard model, we have quarks and leptons. So some people find this a little bit aesthetically unpleasing because quarks and leptons are very separate. They're very, blocky. So perhaps there is something that interacts directly with the quarks and leptons, and that could be called a leptoquark. So that would allow us to have a direct interaction between leptons and quarks, and that, by principle, if it's a leptoquark, lepton quark, would violate lepton number. So violating lepton number means that we can have an interaction that allows us to play around with preferential couplings to different leptons and quarks, and lepton number violation is useful for another reason that I won't go into, which has to do with generating Majorana neutrino mass.
Right.
But we can play around with lepton number. That's why that's useful. But realistically, what we can do is we can generate different couplings between the different leptons, so we can play around with lepton universality too. So lepton universality would then be violated in the interactions between the leptoquark and different standard model quarks as well.
You're a theorist working on these sort of models. Is that what you call yourself?
Yeah. So so I have these hypothetical baby particles called leptoquarks, and my most recent work had been looking at an anomaly in the G-2 of the muon as well as in the G-2 of the electron. Okay. So it turns out there's also an anomaly in the electron. And depending on who you believe, because there was a recent paper that showed that that anomaly could be slightly different. But at the time that I wrote the paper, the anomaly in the electron sector was actually in the opposite direction. So we had the muon sector showing that it was like slightly more than the standard model, and then the electron saying slightly less. So that was an interesting kind of thing that we looked at to try and explain that.
Right.
And the way we did that, of course, if you have an effect that seems to be in opposite directions, you really do have to violate lepton universality because the effects are completely opposite, right? So you would expect they're specific to the leptons, and also they're so different that they're in the opposite directions. So what we did was we assumed that the new physics, so these leptoquarks, coupled preferentially to muons, allowing there to be an interaction directly between the muon and the top quark that generated a one-loop contribution to the G-2 of the muon, and then between the electron and the charm quark, which generated a one-loop contribution to the electron G-2.
Right.
And by changing the values of those couplings, what we could do is generate a fairly minimal model. So a single extension, a single exotic particle with slightly, tuned couplings was able to give us a contribution to the G-2 of the electron and muon in the correct way. So the real original part of our work was kind of saying that in the past, people had claimed that you couldn't do this with this type of particle. And the reason that they thought that is kind of in the same way that if you were to do a calculation of like integrating over a sphere and you tried to do it in X, Y, and Z coordinates, you would have a whole lot of hard time. And you'd say, that's too hard. Yeah. That's non-minimal. That's ridiculous. Why are you asking me to do that? However, if you went into the basis of r, theta, and phi, and then you tried to do the integral, you'd be like, that was really easy. So it turns out that everyone in the leptoquark community, especially the scalar leptoquark community, had said that you were not able to simultaneously do the G-2 of the electron and the muon because they were working the wrong basis.
Right. Yeah, that's a classic one.
Yeah, so everyone was working the wrong basis, and there were a bunch of papers saying that you can't do this, you can't do this, you can't do this. So I worked in the non-conventional basis and showed that you could do that. and that everyone kind of was looking in the wrong direction.
Nice.
So,
I'll do a bit of controversial work. Like you want someone to be a little bit upset with you, I think. Yeah. Or at least that's how I'm justifying it to myself.
Maybe. I think I was just more happy when people emailed saying, "Oh my God, I can't believe we missed that."
Oh man,
where I was like, bless, please don't be angry at me.
So what's your intuition about this? Do you reckon it's going to be beyond the standard model, or is it, a bit even? Could be some systematic thing, or, what's your gut feeling?
So I hope it's something. I feel like you can't work so intently on something like this and not have some hope, right? Otherwise it just gets depressing. But also, if it's not, the amount of model building that has gone into all of this stuff is widely applicable to other areas of physics. So my paper came out last year around the middle of the year, or end of the year-ish. I can't remember, it was 2020. But even in the last few weeks, there's been a lot of what we call ambulance chasing papers, where people write a lot of papers about a result. And often it's adapting like a previous result that has been established in the literature and saying, hey, it can do this too.
Yeah.
And that's good in some ways and bad in others. But one positive that you can see from it is that a lot of people are looking at how different models that exist in the literature are applicable to potential anomalies.
Yeah.
And that shows they often show how you could adapt this in the off chance that there exists a different anomaly that might exist in the future. And these anomalies, we speak about them as anomalies, and it kind of makes it sound a bit like, oh yeah, they're probably mistakes. But realistically, at one point, the anomaly is going to be a discovery.
Yeah.
Soon,
4.2, that's pretty good. That's almost there, right?
4.2 is very good. And the different anomalies in the B meson decays, depending on what type of B meson, there are different other anomalies that even show that the pull towards there being non-standard model physics there could be, up towards 5 sigma. We haven't done an actual single detection that shows 5 sigma, but statistically people have looked at it and said that, it looks like if the results stay consistent with what they input into their statistical models, you should discover something, which is really cool. It's cool new physics, even if it's completely not new physics and it's some interesting, cool systematic thing. It's good that people are able to get to the point where we're playing around with numbers that are 10 to the negative 12. We're playing around with really small effects, but those small effects can be such an interesting, clean test of the standard model that it's an exciting place to be.
Yeah. I mean, I guess dark matter people are always hopeful for new physics in whatever form it could possibly come in.
Exactly. And some people work on dark matter models that are able to also tackle this lepton flavor non-universality too.
Yeah. Do you know anything?
I don't personally. I know some things about it. So I know about people who work on Z prime models. So the idea that there's another Z, but that Z has lepton flavor violating couplings.
I think one of those people is my supervisor.
Yeah. Who is your supervisor?
Celine Bone. She sent cool. A whole flurry of papers about Z prime bosons the other day. It was like a giant interconnecting web, like a conspiracy theory. It was very exciting.
I think that honestly, I think if you were outside of physics and you looked at a lot of the papers, you would think that most of them are interconnecting conspiracy theory.
Oh yeah, 100%.
But the interesting thing with Z prime models is often they're really interesting, really cool new physics stuff, but require a lot more input than a standard scalar model. So that's why so far in my PhD, we're focused on single scalar particles as new physics candidates, but there are much more cool, complicated dark matter containing things that exist out there that are really cool.
I've got a question about this model building stuff. Maybe it's a harder question or a more naive I'm not sure. You can tell me if it's a dumb question. But when we're doing these things, it always feels to me like, we just like add this particle to the standard model. And I guess my question is, like, in my head, the standard model is like so beautifully described by this gauge structure where, the quarks act this way under the strong force because they're under some representation of SU3. Technical words, but okay, we can understand maybe. And then when I'm talking about these extensions that could possibly explain non-universality, are there any that are like really fundamentally sourced? Like you add some new gauge structure or something really deep that's not just like, here's an extra scalar field, but like it comes from something really meaningful. Is that something that people do?
Yeah. So another project that I've been working on looks a lot more fundamentally at the generation of certain exotics from a more fundamental, like the idea that there exists some sort of, say, at higher energies, there was, say, a conserved, discrete group that represented the standard model plus the exotics. And then at some point there is a breaking of that leads to certain, gauge boson, not gauge boson, Goldstone bosons, and etc. And these propagate and interact in a particular way that lead to, say, the scalar elliptic quark being a generated massive particle. So people definitely do work on them, and I didn't do a lot of that model building. That was a collaborator of mine, and I work mainly on the phenomenology of it. But there are models like this. Generally, they're out there. They're a lot more technical.
Sure. They always are.
But yeah, you see how it's very cool stuff.
Yeah, I guess it feels like there's this mystery that's just like there's 3 generations of particles in the standard model and just no reason for it. And so all of this feels like this is all wrapped up in some bundle that we need to, I don't know, pull the strings of and try and figure out somehow. So I was just wondering, like, are more people just working on like the phenomenological side, I guess, where you add particles and see what happens? Or is there like a sort of sense in the community that like this is part of this greater mystery that we're trying to work towards,
I would say that there's definitely a sense of the greater mystery. So one of the interesting things about these certain, we might work on, say, a single particle extension or whatever. These single particle extensions could be known to exist in a greater model. So people have written down models that then generate these single particles, and perhaps those single particles are the only ones that should interact in that more larger model with standard model particles in what we would see at the lower energy and where we're seeing it at colliders at the moment. So I agree. I think that there is often this really, really like insane interest in understanding this regeneration problem. And also, I mean, the one that I find particularly interesting is the different masses. So the mass hierarchy in the standard model is fascinating. Because we've got all these different masses. Beg your pardon?
I was just saying, that seems related to the generation thing. It all seems sort of correlated in an interesting way.
Right. Yeah. And this different masses is what leads me into like working in neutrino physics as well, because neutrinos are orders of magnitude lighter. So trying to understand that and understanding these different masses is a really interesting sort of aspect of working in a flavor that is heaps of fun and definitely a really cool area to be looking into. So I'd say there's definitely a sense of like, how do these feed into those other bigger problems in standard model structure as well?
Yeah, well, I guess I'm sort of reassured to know that, everyone has this idea in mind that, we're not just like throwing in models ad hoc, like we're really like trying to pull it from something quite interesting and fundamental. And then just before we run out of time, I guess I want to ask you to be a bit speculative, because we are a dark chatter channel after all. Do you think there could be any interesting like astrophysical implications, like something weird that stars could do, anything we could observe that might be related to this flavor of physics in some way?
So something I read about recently is looking at like the jets from active galactic nuclei
Okay.
and looking at like neutrino emissions from that, and looking at potential flavor dependent interactions that might happen there that then be present in detections here, which is pretty cool.
That'd be
I'm definitely not going to pretend to be an expert in that one, but apparently that is one way of looking at these sort of things. In terms of like flavor specific stuff, there's always talking about, say, the number of neutrinos. The moment that you play around with flavor interactions and you play around with interactions of, say, the Z boson, we play with the effective number of neutrinos, which of course affects astrophysical things. Yeah, there's lots of really cool stuff. I mean, my favorite new physics potential area, I think the one that I'm really excited about is the upcoming measurements in neutrinoless double beta decay. So trying to understand the nature of neutrinos by looking at potentially how they might interact in these experiments, which is really cool. But yeah, wild, cool new physics that could then influence things we do in the early universe as well as more locally. So,
yeah, wow. Maybe I should get into some of that stuff.
Yeah.
Sounds exciting.
Cool.
Yeah. What's the future of these flavor anomalies? Like, what do I have to look forward to?
Hopefully a discovery at some point in the near future. With Bell 2 ramping up. Well, with Bell 2 ramping up with data collection and analyses coming out, I feel like that's really when we're going to start working. I feel like that's where we're going to start seeing things come out that are closer and closer to 5 sigma. I couldn't pretend to predict when the 5 sigma would come around, but you know, with that, with high luminosity LHC, with all of the smaller experiments, even if they're probably physically quite large, that are around, I would say there's a whole lot of really interesting physics coming out in the next few years, definitely in flavors specifically. Yeah.
Wow. Yeah. Exciting. Yeah, I guess that does about the half an hour. That was an interesting sort of a wild tour. We went in and out of different technical subjects, but it was entertaining. Do you have any last thoughts to leave us with? Do you want to pitch anything or hype up a project you're working on?
I would say wait and see. There's a lot of stuff I've been working on. It's this weird time where you're near the end of a PhD and you're like, I want to work on this. I want to work a bit on this. I want to get this done. So at the moment, it's wait and see how it all pans out in the next few months. I'm excited to see a few things finish up and wrap up, and I'm excited to start a few new cool things as well. So
yeah, maybe if you're going to apply for some postdocs, you give them some shout outs now, like
yeah, please give me a job. I promise I work really hard. Oh god, but yeah. No, it's a weird time to be going into the world of postdoc land, but
yeah, sure. We haven't been able to do much travel down here in Australia, so this is our virtual travel.
Yeah, we're definitely going on a trip today. I'm currently in Sydney, apparently.
Oh, wow. So. It's a lovely day in Sydney. Yep, beautiful.
Yeah, cool.
All right. Well, thanks for coming out to talk to us. Maybe you'll run an interview next time.
Oh, definitely. I'd be happy to.
Yeah.
And thank you for having me.
Yeah, easy.
It's lovely to chat.
Cool. Well, maybe I'll see you in real life next time.
Yeah, definitely. Well, always welcome here in Melbourne. We have disgusting weather. It
hasn't
beautiful.
Been great here either, so we're in the same boat.
That's good at least.
Cool. All right.
Cool.
Thank you.
Thank you.